Welcome back, physics enthusiasts. I'm Swati, and how are you and how your preparations are going? February is already here, countdown has begun, and I really hope that you all are doing perfectly well. So, our series on MCQs continue. Today, the lecture is on magnetism and matter. So, Chal have chapters or baki hai, and again, the questions are really important. They're excellent for last time revision. So, let's begin with that. Okay, students. So the first question is the material which is not suitable for making a permanent magnet. परमानेंट मैग्नेट के लिए अगर हम ऑप्शंस देखें तो इसमें से लेड जो होता है वो डायमैग्नेट होता है. सो डायमैग्नेट है तो इसके अंदर जो अलाइनमेंट है वो अपोजिट डायरेक्शन में होगा, तो परमानेंट मैग्नेट के लिए इट इज नॉट सुटेबल. सो सिंपली सी. बाकी स्टील तो होता ही है. टिकोनल निको कैन ऑल्सो बी can be used to make a permanent magnet. Next is the magnetic needle is kept in a uniform magnetic field. Okay, since the field is uniform, then it experience the force torque and will not. So if the field is uniform, then it only experience torque and there would be no force. Okay, in a non-uniform magnetic field, it experience both. So a torque but not a force. That is option number C. So in third, they have asked that if it is kept in a non-uniform magnetic field, then it experiences both a force and a torque. That is option number A. Just remember that it's the same concept as electric field. A bar magnet of magnetic moment M is placed in a uniform magnetic field of induction B, the torque. It again same as electric field. Like in electric field, the torque is P cross E. Here it is M cross B, where M is its magnetic moment and B is the magnetic field. So C is the correct option. It's M cross B. Next, a uniform magnetic field exists in space in a plane of paper and is initially directed from left to right. When a bar of soft iron basically is a ferromagnet, is placed in a field parallel to it, the lines of force passing through it will be represented. For a ferromagnetic substance, the field lines move from the material, means it is more dense inside the material. So option number B is the correct one. It's not uniform, it's not moved away. This is more like a diamagnetic state, and it goes from left to right. So this is again not. And for paramagnetic material also, some field lines are there, but ferromagnetic, its density is more. It is like that. Now, point A and B are situated perpendicular to the axis of a 2 centimeter long bar magnet at large distance, x and 3x from its center on opposite side. Okay, this is a bar magnet. Okay, and on its perpendicular, you have 2 points, x and 3x on the opposite side. One at a distance x, other at a distance of 3x. Okay, now they are situated at some large distances. So basically it has a formula of magnetic field on its equatorial axis, which is some constant times of magnetic field upon में distance cube. Okay, for large distance. Okay, so the distances are large, so we can simply write as this. Otherwise it is like the length of that bar magnet. Let's take this as a square plus distance square raised to the power 3 by 2. It's same as that we did in electric field. So there is some constant which is mu naught upon 4 pi. M is dipole moment, like kp by r cube. Same like this. Some constant, p is dipole moment by r cube, and here we only need this r cube. That's it. So basically ratio of A and B we have to calculate. So ratio of A upon ratio of B is, for A is x and for B is 3x. So 3x whole cube upon x cube, that is 27 by 1. So 27 is to 1. X cube, we can cancel it out. Okay, if it is not large distance, then you have to use the formula of a square plus x square raised to the power 3 by 2, where A is this, the distance from the midpoint of the bar magnet, and x is this perpendicular distance. Okay, you can check the formula. Okay, the next is a paramagnetic sample shows a net magnetization of 8 ampere per meter when placed in an external magnetic field of 0.6 Tesla at a temperature of 4 Kelvin. When the same sample is placed in an external magnetic field of 0.2 Tesla, find the magnetization. So the formula is basically M by H is basically proportional to 1 by T and is equals to C by D, where C is the Curie's constant. Okay, so for the first, I'm erasing this. You can pause and you can check the solution. So the M will go like this, C by T times H. Okay, so initially the magnetization of 8 ampere per meter. So 8, and we have to calculate the magnetization of the other one. C is constant, so let's take H by T. So for the first, H is 0.6 Tesla and temperature is 4 Kelvin. By 4, let's drop the unit. Then for the other one, H is 0.2, put 0.2 here and temperature of 16 Kelvin here. Okay, so decimal will cancel out each other. 2 1s are 3s are 4 1s are 4 4s are 4 3s are 12. So 8 by x is equals to 12. So x is 8 by 12, that is 4 by 3. Sorry, 2 by 3. That is B. So B is the correct one. Okay. Okay. So in the next question, number 8, you have a long solenoid has 1000 turns per meter and carries a current of 1 ampere. It has a soft iron core of mu r 1000. The core is heated beyond the Curie temperature Tc. Then what will happen? The H of the solenoid is unchanged, but the B decreases drastically, and H and B field in the solenoid are nearly unchanged. Magnetization the core reverse direction. Magnetization the core diminishes by a factor of about 10 to the power 8. Now if I look at H, it is equals to Ni, number of turns into I. Okay, so this remain unchanged, but your B is basically mu H. Okay, so this mu is also if you take mu M, that is mu naught mu R times H. So it depends on this mu R, so there will be some change in magnetic field. So if B remain nearly unchanged, will not be appropriate, it will change. Okay, and for the magnetization also, you know that M by H is proportional to chi. Okay, H here is constant, but that chi is for ferromagnet is proportional to is of the factor of minus is of the factor of 10 raised to the power 3, and chi of paramagnet is of the factor of 10 raised to the power 5 minus 5. So if you take the ratio of both, and from here you can see that magnetization is also proportional to chi, which is susceptibility, then it is equals to 10 raised to the power 5 upon 10 raised to the power minus 5, then it goes to 10 raised to the power plus 8. So the magnetization of the core diminishes by a factor of 10 raised to the power 8, because beyond Curie temperature, your ferromagnet will change to paramagnet. So ferromagnet by paramagnet is equals to 10 raised to the power 8. So it decreases because it changes to para. Okay. Sort of interesting question. Likewise, we will say, okay, there will be no change in magnetization, but magnetization is related to susceptibility. And if there is a change from farad to para, then there is some change in magnetization as well. And you can also understood from this concept that during magnetization, in the ferromagnets, that whole domain is partially aligned, but if changed to paramagnet, the domains break down and the single electrons aligned. So the magnetization it obviously be affected by this. Okay, so in ninth, a bar magnet AB with magnetic moment M is cut into two equal parts perpendicular to its axis. Let's say this is a magnet A and B. It is cut from the perpendicular like this. One part is kept over the other so that the end B is exactly over A. Now, just if let's say A is north pole, okay, it's not given, so let's say north, this is south. When it is cut from its perpendicular axis, that is from here, then this point will become south and this become north. Okay, now A is exactly over B. This is A and this is B. So A is North Pole, that means this is South, and B is South Pole and this is North. So if we look at the direction of magnetic movement, then it is from South to North for the above bar, and for the below it is in opposite direction. So both the magnet movements are in opposite direction, so they will cancel each other, and the net magnetic moment of the combination would be 0. Okay, otherwise you can add them because they are in same direction. So yeah. And if a magnet of magnetic moment M is cut into two equal parts, the two parts are placed perpendicular to each other so that the north pole touches each other. Let's say you have a magnet cuts into two part. So let's say it cut like this. So each part will have a magnetic moment of M by 2, M by 2. And then it is placed perpendicular to each other like this, that their north poles are together. It is something like this. So north to south has one magnetic moment. Sorry, south to north. South to north has magnetic moment of M by 2. Okay, let's redraw it. This is one bar magnet with north, south. This is the magnetic moment. This is north, this is south, south to north magnetic moment. This is the magnetic moment of M by 2. This is the magnetic moment of M by 2. They have an angle of 90 degree. Then you can use the resultant formula, that is M square plus M square plus 2M square cos 90 degree. Cos 90 is 0. This would be 2M square and M is M by 2 under root. Then it would be root 2 M by 2 ka whole square, that is M by 4, and when it comes from under root it would be M by 2. On rationalizing it you will get M by root 2. I hope this calculation is fine with you all. I will do it again. Let's take both this M by 2. So the net magnetic moment would be M by 2 whole square plus M by 2 whole square plus 2 again M by 2 whole square cos 90 degree. So this term will be 0. Okay, this term will be root 2 times of M by 2 square. Cancel out the root, and if you rationalize it, it will be M by root 2. You can always pause the video, and since if you find any difficulty, you can comment below. I will help you out again through any media, but I'll try to help you out definitely. Okay, the next is the meniscus of a liquid contained in one of the limbs of a narrow U-tube is placed between the pole pieces of an electromagnet with the meniscus in a line with the field. When the electromagnet is switched on, the liquid is seen to rise in the limb. If it is rising, it could be ferromagnets and paramagnet. Okay, let's take a meniscus of a liquid contained in one of the limbs of a narrow U-tube is placed between the pole pieces of an electromagnet with the meniscus in the line with the field. When the electromagnet is switched on, the liquid is seen to rise in the limb. Okay, if it seemed to rise in electromagnet, then it is a paramagnet material. Electromagnets are made of soft iron. As for the electromagnets, the permeability, the susceptibility, and the retentivity should be high, and the coercivity and the hysteresis loss should be low. Just remember this. Okay, it's not in CBSE, but for the competitive you should know this. So are made of soft iron because it have large permeability and large retentivity. स्मॉल ससेप्टिबिलिटी नहीं होती है, स्मॉल रिटेंटिविटी भी नहीं होती है. लार्ज ससेप्टिबिलिटी होती है बट स्मॉल रिटेंटिविटी नहीं. स्मॉल परमेबिलिटी एंड लार्ज, सो it should have large permeability and large retentivity. Okay, next, in a permanent magnet at room temperature, may the permanent magnet has domains but they are partially aligned. Okay, magnetic moment of each molecule 0. No, the individual molecules have non-zero magnetic moment, which are all perfectly aligned. No, they are partially aligned. Domains are all perfectly aligned. No, in the presence of at some temperature, it perfectly aligned. If a magnetic substance is kept in a magnetic field, then which of the following substance is thrown out? Only diamagnets. They repel. They don't like magnetic fields. Above Curie temperature, ferro changed to para. Ferromagnetic material become paramagnetic. Okay. In the hysteresis cycle, the value of H needed to make the intensity of magnetization zero. Okay, again, hysteresis is not there, but it has something like this. Okay, now here we have H and here we have B. So this is basically retentivity. This line is for retentivity and this small line is for coercitivity. So if you want to make H 0, if you wants to make H 0, then basically coercivity force should be 0. It is like this. Okay, on this axis it is H, on this is B. This particular line is for retentivity and this particular line is for coercivity. If you want to make H to be 0, then which force would be the coercive force? Okay, next is susceptibility. This is not in CBSE, but okay, you must know hysteresis. Susceptibility is positive for para, it's positive and small. For ferro, it's positive and large. Non-magnetic. Diamagnetic is negative and small. So it's positive for both A and B. Okay. Next question. A bar magnet has magnetic moment M. Its initial position is parallel to the direction of uniform magnetic field. In this position, the magnitudes of torque and force. Since it's uniform, then force would be 0. And it is aligned parallel to the direction of magnetic field. So angle would be 0 degree and torque is mb sine theta. So torque would also goes to 0. C is the correct option. Otherwise, what we will do? We simply mark this one. M cross B is torque and 0 is force in uniform field. But they have given that it is parallel to the direction of uniform magnetic field. A diamagnetic substance is brought near the north and south pole of a bar magnet. It will be repelled by both. Okay, it doesn't matter it's north or south, polarity doesn't matter. It's just repelled by the magnetic field. So repelled by the north pole, repelled by both the poles, attracted by both the poles, repelled by north and attracted by south, repelled by both the poles. So A is the correct one. Next, a magnetic field lines near a substance are as shown in the figure. They are repelled by it. So this substance is diamagnetic because the field lines are repelling. Okay, so in this, copper is a non-magnet. Okay, so this much for magnetism and yeah, छोटा सा chapter है, interesting one, but again it has a lot of concept. Just learn this last thing is the examples of paradiagnets and ferromagnets. Okay, so thank you for watching this video and do like and subscribe for more such videos.